And I think it's time to pass over to our next speaker, who is Sonia Buckley from NIST. Thanks. So if Sonia's ready, you can start sharing your screen.
Let's see. Okay. Okay, well, thank you, Jake, for the introduction and doing a great job of hosting so far. My name is Sonia Buckley. I'm a research scientist at NIST in Boulder in the group of Rich Mirin and Seiwu Nam. And my talk is going to be a little different maybe than some of the other talks in this session, in this workshop, in that it's not actually about quantum information or quantum computing. I'm going to be telling you about our hardware platform for neuromorphic computing. So to start with, I'm going to try to give you a brief introduction about why that might be interesting to people who work on quantum information or quantum computing. And then a little bit more about what I mean by neuromorphic computing before telling you about our hardware platform and our efforts to build the first neurons in our hardware platform and our experimental progress. So to start with, this is an image of a chip made by a group at Bristol for a large, for an integrated photonic chip for making highly entangled photon states. And they had something like 16 entangled photon sources, a few hundred waveguide crossings, Mach-Zehnder interferometers. And the reason I bring this up is because they took some integrated photonic technologies that were developed for classical telecommunications, and they applied it to quantum photonics. And moreover, there are technologies that they developed for quantum photonic technologies. And what I would like to do, or what we would like to do, is to take some of these technologies as well as the classical technologies and use them for other applications. So the main point is that some of the technologies that are used for quantum photonic computing can be applied to other technologies. And I hope you can see during the talk that actually some of the requirements are actually a little easier to meet for other applications. So, okay, so with that, what is neuromorphic computing? So basically, neuromorphic computing is building hardware with the capabilities of the brain. So the idea is that some of the unique processing capabilities of the brain are fundamentally due to differences in its hardware. So the hardware in the brain looks very different to a classical computer. And I'm not the only person, or we're not the only people who think this way. A lot of companies are coming out with neuromorphic chips, things like IBM's True North and Intel's Loihi. But one of our theses is that CMOS hardware may not be the best hardware for neuromorphic computing. And one of the reasons we think that this is that one of the big differences between your brain and a computer is the huge number of connections between processing units or neurons. So in your brain, a neuron can be connected to 10,000 or even 100,000 other neurons. And so we think that because of this massive connectivity, you want to use photonics. Because photonics is really good at connectivity. If you're using photonics for connectivity, what about energy efficiency? So we want to do the communication using photonics, but we want to do the computation using electronics. And so for energy efficiency, then this means we want to use superconductors and superconducting detectors. Okay, so this is an SEM of a single neuron on the left, and then on the right you can see a cartoon image of a neuron. And so just as a intro to how a neuron works, the neuron has a cell body that has a membrane potential or voltage. When that voltage exceeds a threshold, the neuron will fire a voltage spike that travels down the axon, and then it can connect to, like I said, thousands of other neurons at synapses, which weight that voltage pulse. And then the downstream neurons will integrate all the voltage pulses that they receive from upstream neurons, and then decide whether that exceeds the threshold, and if so, they'll fire their own voltage spike. So that's the very simple integrate and fire model of a neuron. There's obviously, as with everything, a lot more complexity going on, things like learning. So to learn, there's something called spike timing dependent plasticity. The rate of learning is even controlled by something called metaplasticity. And then there's, the connections can be either excitatory or inhibitory, and you can have further computation happening in the neuron using dendritic compartments. So there's a lot that can go on. What about our hardware platform? So the main point is that in our hardware platform, the voltage spikes in the neuron are replaced by photonic pulses generated by a semiconductor LED. These photonic pulses are routed around by multiplanar waveguides. And then I mentioned that the computation is done electrically, and so there needs to be optical to electrical conversion, and that's done using superconducting detectors. And then all the computation is done using other superconducting devices, things like Josephson junction circuits, mutual inductors, and then we need some superconducting amplifiers. So since we're using superconductors, we're not talking about building a device that someone's going to put into a cell phone. We're talking about something a little bigger. Let's say you have a supercomputer and you're building a quantum accelerator for it. Well, maybe you also have a neuromorphic accelerator. So, something similar to what Matt said, once you're working cryogenically already, why not build extra computational devices using superconductors? Okay, so that was the brief introduction and motivation. So now, how are we going to build the first neurons? So the first thing I want to point out is that everything I'm talking about today is being done in the NIST clean room. And the NIST clean room is something similar to your typical academic clean room, and all of the fabrication is done by a scientist like me or one of my colleagues. And so, that's a little different than one of these commercial foundries. So the hardware platform that I mentioned, it involves multiple planes of waveguides. It involves several layers of superconducting devices, and then, light emitting diodes, which have a couple of doping levels and so on. So this can wind up being something like a 20-layer process. So that's pretty hard to do in, an academic clean room, basically. And so one of the first things that we thought of when we're trying to actually demonstrate some of these devices is, how can we simplify it, just for a first demonstration? And so with some collaborators at the University of Tennessee and Oak Ridge National Lab, we came up with some simple benchmark tasks. And then the idea is that we test out different models of our hardware with varying levels of complexity to see if we can build networks to solve those simple tasks. And what is the minimum feature set that we need in order to solve those different tasks. So an example of a benchmark task that we were trying to solve is balancing an inverted pendulum on a cart, so the network can move the cart either left or right to balance the pull. And so the networks we're evolving don't look like your traditional deep learning neural network. They have recurrent connections, and it's a spiking network where information can be encoded in things like the timing between spikes or correlations between the spikes, and so on. And we're generating these networks via evolutionary optimization. And so the point is that using this, we were able to come up with a minimum feature set. And so we take our, our full hardware platform and we whittle it down basically to a very simple integrate and fire neuron. Okay, so that's what we're trying to build right now. And so now let me tell you a little bit about our experimental progress towards actually building it. So similar to a photonic quantum system, we require low loss waveguides for routing and things like waveguide crossings. But maybe in this particular case, our requirements are a little more stringent because we have such, we have so many connections between neurons. And so we've come up with these multiple planes of waveguides to solve this massive routing problem. So here's an example of, on the left, you can see a 3D image of a 1 to 9 waveguide coupler. So it consists of 3 layers of amorphous silicon waveguides. So on the right, you can see these are the 3 planes, the middle, the top, and the bottom. So light comes in through this waveguide and then can couple to each of these 9 waveguides with around 0.05 dB of loss in a length of around 36 microns. So you can get coupling from 1 waveguide to 729 waveguides in a little over 100 microns of length. So using this technology, we were able to do these 10 by 100 routing couplers. So in this case, it's using 2 layers of silicon nitride waveguides. So these are all the input gratings. And then here you can see, so each of these could, let's say, correspond to the output of a neuron. And then here, each of these groups of 10 corresponds to 10 synapses at a downstream neuron. And this is a optical microscope image of the experiment. So essentially you couple light in one of these input gratings, and then you see light on 10 output gratings. And they're different levels of brightness because we tuned the beam taps to be that way. In this particular case, we were aiming for a Gaussian distribution, and you can see on the bottom right, each of these blue dots corresponds to the brightness of these white light spots. And you can see that indeed follows a Gaussian distribution. So this experimental technique was an automated image processing technique. Okay, so what about, that's the routing, what about the synapses? So in the full hardware platform, we use these superconducting detectors to convert from optical pulses to electronic pulses at the synapses. And then we use superconducting electronics to apply weights and learning and so on. However, we found in our simulations in the simple hardware platform that we could actually apply weights directly during the conversion simply by changing the bias current on one of these detectors. And so that's what we're doing in this simple version. So these detectors were also used in this experiment that I keep coming back to as my example comparison experiment. Light in this experiment was coupled off chip to 2 fiber coupled SNSPDs rather than waveguide coupled SNSPDs. So I'm assuming that most people at the conference know about superconducting nanowire single photon detectors, but just very briefly for people who don't or need a reminder, the detectors consist of a thin film superconductor that's patterned into a narrow wire. And then an incoming photon breaks Cooper pairs in the wire and creates a hotspot. So these wires are also current biased. So then that hotspot grows via Joule heating, turning the whole width of the wire normal, and generating a voltage pulse before cooling off and the wire returning to its original superconducting state. So this is what, so for a good detector, this is what the count rate versus bias current curve should look like. So as you increase the bias current on the detector, you start detecting photons, and the number of photons you detect increases as you increase the bias current. This is for a constant light level, so the number of incoming photons isn't changing. And then at a certain point, you're essentially detecting all of the photons, and so the count rate doesn't change anymore with bias current. So you have this plateau where you essentially have unity internal quantum efficiency. And so the idea here is that the pulse height changes in this region, but the detection efficiency doesn't. And we can use that as a simple weighting scheme. And furthermore, this is just a good way to operate your detectors. You know that the efficiency will be very high and constant, and any jitter in your bias current doesn't change your efficiency. So this is an example of an integrated device using these detectors. So here we have an input grating. So light is coupled in here, and then it's split at each one of these 50-50 beam splitters. So light comes in here and it's split ultimately 8 ways. One of the ways is an output grating, and then it's divided evenly to 7 different detectors. So this is similar to what you might do in a neuron. So if you had a neuron branching out to, let's say, 7 other neurons. Okay, so at the neuron itself, if a sufficient number of neurons, upstream neurons fire at once, then the neuron should exceed a threshold and fire its own pulse. So what does this thresholding operation and the LEDs, which I'll talk about in a minute, also require some gain. And we need some superconducting amplifier / switch to perform these thresholding and gain operations. And so these elements, these kinds of superconducting amplifiers or switches are of interest more or less anytime you're doing any kind of computation with superconductors. Here is an example of using it in a memory element for superconducting computing in a recent paper. Okay, so the firing mechanism in the neuron is conceptually relatively simple. So you have a superconducting branch in parallel with a semiconducting branch. So say this superconducting branch is a nanowire detector, and they're current biased. When this branch is superconducting, all of the current goes through the superconducting branch because the resistance is 0. When it detects a photon or is triggered somehow and turns normal, the current is now diverted to the semiconducting branch, in this case an LED, which could fire a photonic pulse. So in principle, that's great, but in practice, if you use a typical superconducting nanowire detector for this, when the superconducting branch turns normal, actually you only generate about a kilo-ohm hotspot. So do a little bit of math. Typically you bias it with around 10 microamps of current, and so that leads to around 10 millivolts of voltage. Now a typical LED, or our LEDs, require around a volt in order to fire. So it doesn't work, basically. And this is sort of a fundamental problem. There's a mismatch between the superconducting band gap and the semiconductor band gap. So superconductors, you know, it's really hard to generate a voltage with superconductors, essentially. So this is where we need a voltage amplifier. And so the idea is that is that if you can heat a large enough section of the superconductor rather than just a small hotspot, then you can generate a high impedance. And so the device consists of what's essentially a hot plate resistor separated by a thin layer of dielectric from a large superconducting meander. And when you heat up the hot plate, then you heat up the entire superconducting meander, and you generate a high impedance around a megohm, and therefore you can generate a volt. So now what you have is you have a detector that's in parallel with this amplifier switch, which is in parallel with the LED, and so you can provide the amplification needed for the interface. Okay, so the final thing I want to talk about is the LEDs themselves. And so a neuron fires when a silicon LED fires a photonic pulse down a waveguide. And so in this photonic quantum chip, there were 16 spontaneous four-wave mixing sources on chip. And part of the reason this was so impressive is that it's really hard to make a lot of indistinguishable quantum sources with high purity and high heralding efficiency and so on. We have very different requirements. We don't require a quantum state. A thermal state is fine. We'd like it to be electrically injected so that it can be triggered by the neuron. We actually require cryogenic operation because we're using superconducting detectors. We want to be able to fabricate thousands on a wafer. Our efficiency doesn't have to be that high. We find that if we can get 10 to the minus 4, then we can start to build large-scale, interesting systems. And the lifetime should be around 10 nanoseconds. So we're building silicon LEDs, which sounds strange because silicon is typically a very poor light emitter due to the indirect band gap. However, working at cryogenic temperatures helps you because it turns out there are emissive centers in silicon that similar to the nitrogen vacancy center in diamond can emit light. So the ones we're talking about are W centers generated by ion bombardment of silicon and silicon. They emit at 1220 nanometers with a lifetime of around 30 nanoseconds and operate below 40 Kelvin. So the idea is to implant them in the I region of a PIN diode, and when you forward bias it, you generate light in a waveguide. So this is an optical microscope image of some devices that we fabricated. And you can see it's a cryogenic optical link with a LED on one side, a detector on the other, and you get 40 dB suppression of detection of counts on a detector that's not on the waveguide. So we get a total system efficiency of around 5 by 10 to the minus 7 with these devices, which isn't the 10 to the minus 4 we were aiming for. But recent results of varying the implant energy in SOI suggest that we can get something like 2 orders of magnitude improvement simply by changing the implant condition. Finally, we're moving towards fabrication at a larger scale, which you really need to do if you want to build large-scale systems. So this is some data in collaboration with SUNY Poly, where they implanted W centers at a 300 millimeter wafer, and we saw pretty good cross-wafer uniformity. So with that, just to summarize, this is a new application for technology developed for quantum photonics. We're working towards demonstrating networks, and there's additional functionality we can demonstrate if we can add new hardware additions that I don't have time to talk about. And thank you for your attention.
Thank you very much for the talk. Yeah, it's really great to hear about people who are, scaling photonic technologies in cryostats, beyond our own field. So it's really nice to hear about that. So maybe we've got time for one question, and then the others will have to go onto the Slack channel. Brian Flynn asks, how do the neuromorphic processors compare to intelligence processing units, which are specialized hardware for neural networks?
I mean, this is more or less just another flavor of that. A lot of those are trying to do deep learning with sort of specialized hardware. So they're essentially building ASICs for deep learning. This is different in that we're starting by seeing what the brain's hardware capabilities are and seeing if you can develop hardware that can do the same things the brain hardware can do. And it turns out that's really hard. It's really hard to think of physical hardware that can branch out physically to 10,000 other connections and signal and do all the things the brain does. It's really eye-opening to think about that.
Yeah, sure. So there's actually a lot of questions on Slido, and sadly we don't have time to answer them, but I really hope that discussion can continue on the Slack, because it looks like it'd be very interesting. Yeah, so thank you again for the talk.